Yeah, so very warm welcome everyone to this session of the virtual lab with Professor Jackson Said from the University of Malta. He is actually coordinator of the Cosmoverse Action, the COST Action, that collaborates with Cosmos Network. And he will talk about addressing observational tensions in cosmology with systematics and fundamental physics. Thank you, Jackson, for being here.
So thank you so much. Thanks for the kind invitation. And yeah, so what I hope to do today is to tell you a little bit about what we're doing in this nice new network related with the growing problem or growing question of cosmic tensions or tensions tensions between surveys in cosmology and how we can address this using either systematics or new models, new formulations of fundamental physics. I guess the first thing to say is, why is this important? Why is this more important than the other things that we have in cosmology? Because there are and there have been open questions for many years, decades, on questions that we have about the fundamental nature of the standard model of cosmology, the source of certain things from dark matter, dark energy, finding them directly, all the way to quantum gravity. But this is much more, let's say, in your face. It's not something that you can, in a sense, run away from and say, all we care about is explaining observations, because this comes from the observations. And in this nice quote here by Adam Rees, the H0 tension or the value of the Hubble constant today, currently, is really, one of the best end-to-end tests for our standard model of cosmology, which we call lambda CDM. Lambda for cosmological constant and CDM for whole dark matter. Or, here we're talking about the philosophy of these models, so we can just say dark matter. And really, this is a tension between different kinds of observations, in a sense. It's not a tension that we have within observations themselves. It's not as though we get a data set and it's inconsistent in and of itself. It's that when we get two kinds of data sets, that in some cases they are in tension with each other, meaning that they give us different values of this Hubble constant. And this Hubble constant, it is the value of the expansion rate today, the current value. However, more than that, we can think of it as the culmination of the entire history of the universe and how that gives us the value we have today. That's why we call it an end-to-end, the best end-to-end test of our standard model of cosmology. And what are these different kinds of observations? One way to look at it is, if we're looking at the data sets themselves, we'd be talking mainly about the cosmic microwave background radiation, so the first light we have in the universe, versus the first recorded survey of seeing this was the Schultz measurement in this first bullet point here. But we can think of this as supernova data sets. However, this has grown since then, and now it's become a problem related. We can think of this as early time, or time related to the very early universe, around about the time when the universe became transparent to light, and CMB, but not only CMB, versus late time measurements. So not only just supernovae type 1a, but also type 2, gravitational waves possibly, quasars, many other things beyond that. And now in the coming year, we hope to have a white paper that really goes into detail on all of these new measurements that are coming online related to that. So what do we need to change in our standard model of cosmology? Where are the weak points and where are the positive things? So just to think a little bit about our standard model of cosmology a little bit, just to remind ourselves. And again, I know that this is a philosophy audience, so feel free to stop me if something goes a bit too much. But when we think about our standard model of cosmology, so the way that we describe the universe, what are the ingredients? This is the question. What is the thing that's going into this model that is problematic? So if we think about this, there are some basic ingredients that we throw in this soup to explain the universe, right? One of which, the bedrock of this, I would say, is generativity. So Einstein's theory of generativity, which gives us a way to explain gravitation. And this is what we depend on to express gravitation throughout the history of the universe. Obviously, on top of this, we throw in the matter that we can observe, the standard model of particle physics, which has unparalleled success in explaining all phenomena, as far as I can see, almost um, in particle physics experiments and beyond. Beyond that, what else? What else can we put into this? Well, if we think about the very early universe, so when we're thinking, so here I call the concordance model, or another word for our standard model of cosmology. If we're thinking about the very early universe, in a sense, on the positive side, we have, or more than positive, on describing the standard model of cosmology, we have the need for something called cosmic inflation, which is there to explain some issues in the standard picture of the universe. They're called the horizon and flatness problems. So these are questions of why does the universe look so isotropic, so uniform across the sky? That's one question. Another one is, why does it seem so what we call flat? So generativity explains gravitation through curvature, and the universe seems very consistent with being flat. So there are these questions that cosmic inflation can help explain a little bit. On the other side, we have some what we can call anomalies, and there are many questions. Now, these are not make or break, in the sense we're not at a breaking point in the theory, but they are at a significant statistical tension that we can ask. We can call them questions, let's say. And these include, right here I write the lithium problem, but this is a broader question about Big Bang nuclear synthesis. So are the ratios really consistent with a lambda CDM evolution of the universe? That's one question. There's also questions about hints of maybe the universe is not totally flat. Maybe it has some curvature, and if it does, it seems it may be that the curvature gives us a closed curvature. Then there are a number of questions here related with the CMB. So again, there are in our standard model of cosmology, we assume that the universe is isotropic and homogeneous, but there are some further questions beyond that. For instance, why don't we say large-scale anomalies in the CMB? Things of this nature. Staying on the CMB, we can think about things like birefringence, which is something which is relatively new related with this. Now, just to say these, and there are others, these are all issues related with the very early universe. So in addition to tensions, it's not that everything was great beforehand. Then on the other hand, we can look, and these are maybe a little bit more popular, we can look at the late universe. So if we're looking at the late universe, the only way that our lambda CDM model works is if we add into it dark matter, first of all. Mostly this will be cold dark matter, meaning that these particles, they won't be as energetic as to escape a galaxy or a galaxy cluster. And when we say dark energy is an observational fact. Within lambda CDM, we interpret this to be the cosmological constant. So it's a very exact model of dark energy. But dark energy may express itself in other ways. So we have these things. But then on the other hand, there are some, let's say, long-standing issues related with this. For instance, mentioning dark matter, and really explaining the density of dark matter within galaxies. For instance, at the core, is there a higher density or lower density? We call this the core cusp problem. When we take cold dark matter, in simulations, there's also many times a prediction of having a lot of what we call satellite galaxies. These are smaller galaxies around a main galaxy. And these we don't see in the real universe, but that they appear quite frequently in these simulations. Moving on to the other thing I mentioned, dark energy. Dark energy, I mean, okay, we can call it the cosmological constant, but that doesn't explain anything in a sense. What is the fundamental nature of this cosmological constant? Where does it come from? Is it quantum gravity, for instance? Is it something classical? Where is this coming from? There are these questions, let's say, which again, we can learn to live with, let's say, but the H-naught tension goes much more beyond that, because it's not that we cannot explain some of the fundamentals of the theory, but beyond that, we're having issues with the with, with the prediction of some of the parameters that come out of this model. And to come to it, at this stage, when we talk about, let's say, the value of the Hubble constant. So now we've mentioned it as an idea in principle, but going into the actual value. So here at the bottom, I give these two values. There are many values of the Hubble constant, and now in some other graphs, or some other slides, I'll show some of those. But just to paint a picture, if we take from the European Space Agency, the Planck mission, the last results that they had, which in conjunction with lambda CDM give us a value of the Hubble constant. When we look at the CMB, we cannot just pry away a value of the Hubble constant. We have to put a model into this. It's not something we can do without having an idea of how the cosmological evolution works. Otherwise, this problem wouldn't exist. But putting all of this in, we get a high 60s, and as you can see here, 67.27, with a very low uncertainty, that plus minus, of kilometers per second per megaparsec. Now, this is a number that depends on lambda CDM. And if we had to have another model, we could get another value, granted. But we cannot have a value from the CMB without putting in some cosmological model. On the other hand, here we're seeing this S22, this SHOES 2022 value. And this is in the low 70s, 73.04, with again, a very low uncertainty. This is very different. In this case, there's no assumption of lambda CDM, but there is an assumption of the underlying astrophysics that's going on when we make these measurements. Now, this relies on a combination of using what are called Shepard variable stars to calibrate distances. And on top of that, these supernova type 1a that I mentioned earlier, these stars which undergo this gigantic explosion that really let us estimate their distances using a standard candle approach. But the main point to take away is the distance statistically between these values. Now here, what we're seeing is a big compilation of many, many values of this Hubble constant. Now, just to note, there are so many here, it's very difficult to even see that text. It looks so, it's so small, it's pixelated, which tells us quite how firm we are that this, it may be down to what we call a systematic. It may be down to something we're not understanding either in the astrophysics, in the cosmology, in the instruments, or something along those lines. But if you see each of these subsections have different colors, and these are all different kinds of measurements. That's one thing to say. Also, in vertical here, we're seeing those two values I mentioned earlier, or an estimation of them. And on top of that, we're seeing in horizontal, we're seeing the values of these different surveys that were done using these different techniques. At the top, what we're seeing are measurements, we call them indirect measurements. These are measurements which rely on assuming lambda CDM, and they are by and large from the early universe, mostly related with CMB, but not only. There's also some that don't. And if you see consistently, they are all very much on the lower end of this H-naught value. Whereas the ones at the bottom, and there are more of them, these rely, on understanding some astrophysics, but they don't rely so much on having a cosmological model. And another way to look at this, what we're doing, one thing we're doing in this action is trying to see different ways of interpreting this tension. So I mentioned phenomena precisely, so supernova type 1a and CMB that I mentioned early and late. Now I'm mentioning indirect and direct. And also here there are these two relationships, which is another way of looking at this. RS has got to do with what we call the sound horizon, which has got to do with if we imagine the universe before before light could flow freely, before it was transparent, we had matter, baryonic matter, which would undergo, since it was like a fluid, it would undergo things like sound waves moving over them, energy moving over them. And at the point when the universe became transparent to light, these rippers, these sound waves froze out. And in a sense, we can measure that radius. We call that the sound horizon. And this will have changed over time. But we can measure that over time and try and work backwards to understand what was going on in those times. On the other hand, at the bottom, we care more about distances using standard candles, different kinds of standard candles to measure distances and to try and relate that with an evolution of the Hubble parameter. So not just the Hubble constant at one particular value, but the Hubble parameter over time. So maybe we'll have a problem. Let's think. Let's take this. Once we have an extraordinary claim like we have with the Hubble extension, let's think a little bit. Could there be an issue, a mistake? This could always be the case, right? But let's try and think about this a little bit. So one thing to think about, I mentioned CMB a lot, cosmic microwave background radiation. There's a lot of details here, but not to talk so much about the details themselves, but to pinpoint some important things. So here there's a paper, which is the main cosmology results of the Planck collaboration, their last publication on this point. If you notice here, I highlighted the Hubble constant rho, where again, we're looking at, in this case, 67 kilometers per second per megaparsec. And also at the bottom, there's that whisker plot I showed earlier, and you can see exactly where the CMB results are. Could there be an issue here? So remember, this relies on lambda CDM. So that's one of the main things of that. However, there are other measurements which rely on CMB. Down here at the bottom, I sort of expand that out a bit and I show some updated versions of this. One of the very interesting ones of these is, for instance, this ACT survey. And if you notice down here, if you see these values, again, they're super consistent with each other. CMB is telling us one result. It's giving us a unified picture of having this high 60s value of the Hubble constant, right? You see all of these different, consistently with different combinations, we're getting this sort of value. So that's one thing. But the question may be, maybe we are not understanding something related with the CMB. So let's think, what else do we have in the early universe? One other thing we have, and I mentioned it already, is something called BBN, so Big Bang nucleosynthesis. This is the process by which the nuclei that fill the universe came into being, came into existence. And there was this very nice analysis some time ago related with trying to, independent of CMB, trying to use those ratios, those nuclei that are coming into existence to try and get a measurement of the Hubble constant. And again, if you look at this, look at this table at the top, it's not so important what the differences are between these different combinations of data sets. But the thing that's important to understand is that this is coming from the very early universe and it's independent of CMB. So we're sort of eliminating one potential pitfall in these analyses. And again, like we get this high 60s value. So it's not that CMB is telling us that we want this sort of value, but we're getting a picture from different phenomena from the early universe. When obviously, I always have to keep in mind when we put in this lambda CDM model. Let's think about the other side of the coin. So let's think about the late universe. Again, to start off from a known position, not to go into all the details of all of this, but again, to mention the shoes result, and there are other results that are consistent with this, we get a low 70s value of this H0 value. And something else to understand, in the paper in which this announcement was made, there were checks made, many checks related with trying to understand whether if there were variances and basically in the way that the processing was done, whether it's calibration. There are many things. In fact, here there's an example of, well, not an example. Here there's a list of the 12 different things, the 12 different variants that they changed to try and see if changing these things would change ultimately the value of this H naught result. And it varied little to none, essentially. So again, from the shoes result from type 1a supernova, we're really getting one value, one low 70s value of this. On the other hand, let's think about other things in the late universe. And this is where things get a little bit more complex. So here I'm sort of picking 4 things, 2 from the early universe and 2 from the late universe, where we look at values of H naught. And here I'm just mentioning the most relevant. There are many others, as I mentioned earlier, and as we can see in the whisker plot. So here I'm mentioning something called the tip of the red giant branch. And this has got to do with a turning point in the way that red giant stars evolve over time. So here we're looking for a turning point in a specific type of graph called the Russell-Hertzsprung diagram. And this has got to do with how stars behave and how they evolve over their lifetime. What's nice about these stars is since they are a little bit older, they are not always they are normally off the galactic plane. So it's much easier to see them. There's less dust. That's why these have some advantageous qualities. And during the time that we had this measurement of a high H naught value, there was also this competing measurement from this tip of the red giant branch that gave a lower tension, as you can see here, this F22 value, a lower value of the Hubble constant in the late universe. Recently, there's been this other study at the bottom here that you can see. I think it's been published since actually, I think I need to update this slide. But this now pushes us to a higher value of H naught from this side, or from this tip of the red giant branch, telling us that in the late universe we have a unified picture-ish of this higher value of H naught. So now we have this clear in our mind. We have very clear what this tension is. It's late universe versus early universe, which is very different from just thinking, we have these 2 inconsistent surveys, maybe it will go away. It's really something much bigger than that. And okay, here's another picture of just seeing how the value of H naught varied over time, especially here on the left. You can see how the early universe measurements in pink, slowly as the uncertainties got smaller, they really diverged from the orange ones, which have got to do with the late universe. Over time, there was a real divergence of breaking these 2 things apart. So that's what our attention is all about. That's the source of what we're talking about. Now, what about possible solutions? Now, as physicists, we have many, many ideas. There's an unbounded model space of ideas that we can come up with. So here I'm just going to mention some things that people are thinking about, and some interesting analyses, cherry picking some things which have gained some momentum. The pros and the cons, let's say. Here I'm showing an interesting paper from some years ago, which was given a nice name about the Olympics of the H naught tension. And the whole premise of this is to try and fit some cosmological models, not just lambda CDR, but some cosmological models against each other, and to try and see how they compete statistically against each other. So with 3 different methods in this case. And again, not to go through all I know this is a philosophy series, but just to mention some of these have got to do with different theories of dark matter, how dark matter works, and how the interface between dark matter and dark energy may express itself. There's also some models here which have got to do with what's called early dark energy, and this I'll say a bit more on later on. There's different kinds of having dark energy, not only as a cosmological constant, but also maybe something that varies in time, that has some dynamical qualities to it. And that's what a lot of these are about as well. As well as having different kinds of particle physics. Like, for instance, in the standard model of particle physics, we have 3 kinds of neutrinos. But maybe beyond that, there are other exotic kinds of neutrinos that may play a role that can alleviate or reduce in some way this tension, this H0 tension. So to try and build up to how do we design these models? Because it's not enough to have just 1 million models, we can come up with many, many models, but they need to really impact our cosmology in a way, ideally in a way that we can design, that we can pinpoint. Even before the H0 tension, there have been decades of work on trying to put together new cosmological models, new particle physics models, new gravitational models, models about dark energy. There are many. But here, what we want to do is want to try and see this through the lens of their action on this early and late time dynamic. So when we're thinking about the early time modifications, let's say, before I mentioned RS, I mentioned the sound horizon. And where does that come into this? So one way to look at this is through what's called the angular size when we're looking at the CMB. So I mentioned those sound waves that are moving outwards. Now, in this nice picture here, we can think of this as like a triangle to try and simplify this dramatically. And if we think about this, that angle, that theta s, which is the angular size of these sound horizon oscillations, let's say, and this is something that we measure, that is fixed. But from this, we get, like I have in this literary expression over here, I get a sound horizon, which also in green here depends on the Hubble constant. So if you look at this, if I make one bigger, then the other one will have to get smaller to keep that theta s the same. So this is the game we play. And now in the next couple of slides, I'll come back to this. Well, what's the other side of this? So the flip side of this coin is the late universe. Now, the late universe, obviously, it's somewhere where we have a lot more data. We can look out, we can make measurements, and we can really refine very much these data points. Here, again, there are ideas, but it's much harder to have variances because we have so much more certainty. But saying that, there are a number of ideas, a number of proposals about having late time solutions. To mention a few that we have here, for instance, we can propose what I mentioned earlier, interactions between dark matter, dark energy, having multiple different kinds of dark matter particles or different kinds of dark energy that interact with each other. There's also the idea of having graduated dark energy. So in this case, you would have a cosmological constant that would change sign, which may make us think very differently about things. There's a lot that we can do with this. But again, what are we doing here? Here we are changing, in a sense, we are changing the value of the Hubble constant by fixing it at the very edge of our cosmic evolution. On the other hand, if we're thinking about the early universe, if we're fixing our theta s, our angular size, then let's think about it this way. If we try to design models that give us a higher or lower, in this case, we would want lower sound horizons, lower RS. So whatever your model is, whatever the fundamental physics is that goes into it, if it gives you a lower RS and you are fixing it only in the late universe, only in the early universe, then you can get a higher H0, a higher Hubble constant. And this is one interesting way to fix the issue because you can hide all of this new physics. You can hide it before CMB, in a sense. Or not hide, but you can put all this exotic physics there so that all the measurements you have after that these remain almost lambda CDM, or they remain very, very standard in nature. Because once you start to go very far away from the standard model, the cat is out of the bag in that sense. So there's lots of things that could happen there. And again, sorry about the details. I know that this is a philosophy series, but if we see this picture here, in particular at the bottom over here. So here I'm giving the example of what's called early dark energy, so EDE. And just to put your mind into it, so basically what we're doing is we are imagining this as a bump that happens right before the CMB, right before the universe becomes transparent. And here we're seeing it against redshift. So right now we're at redshift 0, and here we're talking about having this before CMB. before redshift 1100. That's when that would have happened. So here again, it's not so much that we're hiding it, but we're putting the exotic physics in the time when we know exotic things took place, when the universe was in this very high state of energy. And as you can imagine, there are many ideas of early dark energy, and some involving multiple scalar fields, different kinds of potentials, different varying degrees of motivation, some coming from things that we know and some no. And over here in the graphs, you can see, especially like in the middle one, you can see the value of the Hubble constant. And you can see that this is pushing us very close to this high value, but not exactly the high value that we have from the Shoes thing. And this is one of, again, I'm just mentioning the pros and cons, the controversies in this. And just to mention, so far I've mentioned the pros, let's say. On the negative side, there is one issue with this, important issue to mention. There are others, but one very big one. And it comes out in this graph here, but it's a very simple issue to understand. So if I have a universe which was expanding faster before CMB, what that tells me is that there will be an effect on the formation of large-scale structure in the universe. And that means that, so I am gaining having a higher H naught, a higher value of the expansion of the universe today, but I am losing large-scale structure in the early universe. So I have to give something up, and that's what this picture is showing me here. So in green over there, I have the Planck data. Let's call this like the region, the parameter region of the value of the Hubble constant and this radius that we've been talking about. In purple here, I have what's called baryonic acoustic oscillation data. So this has got to do with those sound waves that I was talking about. And then in gray, I have the Shoes result. So that is the value of the Hubble constant from these supernova type 1a and Sheffield variables, that combination of data. If you notice, these never overlap. So the important thing to take away from this picture is that those never overlap completely. And this is the thing that is problematic. So it could be that we have some kind of exotic physics in the early universe, but it seems we may need something in the late universe, or maybe in systematics, but we need something else. This is where it seems to be, where the community seems to be at the present moment. So what else do we have? We're talking about solutions here. What else do we have? So something else we have is possibly other modifications. So one nice guide to looking at different kinds of modifications is something called Lovelock's theorem. So in physics, we very much like to have what are called second-order equations of motion. This is prevalent to all other topics in physics, so we would expect that to happen in cosmology. And Lovelock gives us a way to retain second-order equations of motion, while basically saying that lambda CDM is a unique theory, unless we add something. And there are things we can add, some more exotic than others. We can add things like extra dimensions or less dimensions. We can add emergent terms. So these are things coming from quantum sources, let's say. You can also look at other gravitational or other geometric frameworks. So in generativity, we're talking about curvature, but there's also, we could look at torsional or something else which is called non-metricity. And these are all different kinds of geometry. Very popular also, we can add different kinds of scalar fields, like early dark energy looks like a scalar field, or multiple scalar fields. But we can add other things like vector fields, tensor fields, we can add things there. And similarly, staying on quantum stuff, we can add what are called non-local terms. Or we can go beyond second order and see what happens there. So anyway, so in each one of these things opens up many times. Here I'm just showing a few, and already there's a lot here, so it's not possible to explain all of these in the time we have together, but we can open it up if we wanted to, and it would go on and on. So that's sort of the state of our solutions at the moment. There are some which are very promising, but we don't have a model that we can say, okay, let's forget about Lambda CDM and move on to this other model. We don't have this sort of smoking gun at the moment. So staying on, the question of what if. So what about other kinds of tensions? So we mentioned some anomalies, we mentioned H-naught tension. Just to mention, there is another tension, maybe the wrong word at the moment, but another open question, let's say, which has got to do with what's called the large-scale structure of the universe. And this we characterize by what's called S8. So the value of S8, this embodies the variance of large-scale structure on the universe, on the cosmological scale. And its value, again, has been a big question, but not as big as the H-naught tension. In fact, if you see here in this whisker plot, you'll see that if we take in this case, we're seeing the Planck 2018 value in vertical there. So if we take this value and we compare it with other surveys, that there is quite there's a statistical difference, but it's not at the level of H-naught tension. But this is something to watch as we have Euclid this year coming out with early results. This is definitely something to watch as we're going forward. So that is it, I would say, for the tensions and possible solutions. What else can we do? So this, I don't know how interesting this is for you, but here we're talking about different things which are coming out of the Cosmoverse cross-section. So one other thing that we're doing in this Cosmoverse cross-section is to look at new ways of developing models to tackle this open question. And as with most topics that touch data these days, machine learning is infiltrating into this. And this is still a big open question. So here I'm just going to give you really just one rudimentary example that we have from our research group. But there's a very big potential of new results coming out. But again, I'm just showing you one example that I think is very easy to connect with. So just to put you in the picture. So before I mentioned that, that we have curvature from generativity, but there are other kinds of geometry. One of these is torsion. Normally torsional theories, we call them teleparallel. And here I'm just showing just one rudimentary example of that. This is called f of t gravity or f of t cosmology. And here again, we're changing curvature with torsion. Now, in this case, there's a question about what is the value of f of t, or what is the expression, the model of f of t. So if we're talking about like what can machine learning in the future give us, and maybe philosophically this will be interesting, because here the answer is the model, whereas before we take our model, we run our machine, our data analysis, and we get these answers out for different values. So here maybe this is interesting in that sense. So not to talk about all of these details, but here what I'm just showing is that we take this model, we invert it numerically, such that we want that this f of t, whatever this f is, that it is the answer, it is the thing that we get out of this. And what we want to do in this case, and this is just, again, I want to emphasize just one example. Here what we're doing is we are using neural networks, machine learning. So we are putting into this, we are training some machine learning algorithms, so artificial neural networks, ANNs, such that we get, what do we want in these things? We want this to output my model, my f of t. Now, it's not going to give me a nice expression as a human would, but it will give me values. And then from those values, I can build an expression. And okay, this maybe no, but okay, so maybe from here. So here what I'm showing you is, so obviously those points are the data points, different kinds of data points. And in this case, we're looking at late time data, so from our local cosmological neighborhood. And these have got to do with different phenomena. Maybe it doesn't make sense to go into it right now, but it's based on those baryonic acoustic oscillations I mentioned, but also on something called differential aging methods of galaxies. So this is another really nice method to try and pry out the rate at which the universe is expanding. And the blue curve, the colored curves, basically, these are actually generated by our machine learning code, our ANN. Anyway, what can we do beyond that? So I said that we want to get out of this our model. These are this is it's going to take years to get this to work properly. But already here we can see in these regions, darker regions are the more confident regions. We're seeing the value of that f of t that I mentioned, in this case against t. And it's very nice because already here we can see the potential of this tool, that out of this we can get, if I want different kinds of f of t expressions, I can see how would they fit into this. Are they more realistic or less realistic? The model now is the output. So this is very nice for that reason. So to bring it all together. So what are we doing in Cosmoverse? In Cosmoverse, we are trying to connect all the people who are working on these different things, both on, or we're trying to get people who are working on the observational side, getting more observations, more precise observations, trying to connect that with fundamental physics, so like early dark energy and all those other many early universe solutions, late universe solutions, all the different ways of developing these different models. And also looking at different kinds of data analysis. Can it tell us more about systematics? Can it tell us more about using different new novel kinds of doing data analysis, like machine learning? And here's a nice picture of us in Lisbon. So in fact, we had some nice, we had Marco, right, from this network. So very nice. And yeah, so that is it. So yeah, hope that was interesting. If you have any questions, feel free.
Thank you very much, Jackson. I mean, you touched many issues. Thanks a lot. We can open, of course, the discussion, the Q&A. If there are clarificatory questions as well, they are more than welcome. Hello, Anastasia. Welcome.
Hi.
Are there questions for Jackson?
Can I?
Yeah.
Sorry. I just wanted to thank you very much. It was very interesting talk. I wanted to ask about possible solutions. So you very briefly went through the modified gravity options, and you also said that we don't.
It froze. I don't know if it's me.
Yeah, she's frozen. Yeah, you're back now. So...
Oh, sorry. So yeah, my university Wi-Fi is not the
best. Don't worry.
So I wanted to say that, yeah, you talked about modified gravity solutions, and you said that there is no alternative to lambda CDM that would be good enough for us to abandon lambda CDM, right? So and do you think that all of those versions where they add new fields, for example, or so all kinds of possible alternative gravity models, do you think none of them are good enough?
I don't think, it's not that I don't think that they're good enough. I mean, just to be clear on this, so here we're talking about different things we can do to lambda CDM. We can add fields, we can add dimensions, we can change the geometry. It's not that they're not good enough. It's that there are some points to keep in mind. First of all, we have had a lot of decades of people developing modifications of gravity, different kinds of modifications of the standard model to tackle a different issue, to tackle things like the source of the cosmological constants, to tackle things like what is dark matter. The motivation in those cases was different. Now we have a new issue, we have a new problem that these models were not built to tackle. Now they may be suitable with more development. More development means, really trying to perform more data analysis, see if they match up in a sense. So that's one thing. We only have so many hours of daylight in a sense. But even if they don't work out, and there are a number of promising models, it doesn't mean that the fundamental assumptions are incorrect. What do I mean? I mean, it doesn't mean that adding scalar fields is a bad thing. It could be that we can put together a scalar field that somehow at some point gives us the right solution for the problem that we're talking about here. We are just at the beginning of this. What I'm trying to say is that we need to look at these models not through the lens of do they explain this or that better? Do they explain the quantum nature of our cosmology? Do they explain the nature of dark matter or dark energy? What I'm saying is we need them to give us a unified or more consistent analysis of these data sets. When we say Hubble tension, what we're saying is that there are not tensions within a data set, but there are tensions between data sets. So what we want is that we want a model that really, no matter what survey I put in, that the results that come out of that they are always consistent with each other, which is the question that we have with Hubble tension, that if we do that for lambda CDM, we get out different results. So if we don't put in lambda CDM, we get, and the late universe, we get a high value of H naught. If we put in lambda CDM and look at CMB or BBN and these sorts of things, we seem to get a lower value of H naught. And as time goes on, it seems the statistical difference between these values is only becoming larger. So right now, we don't have a model that is a smoking gun, but it doesn't mean, when I say that, I don't mean that all the models are bad. What I mean is that there are some models which haven't been checked against the data, for instance. Let's say it in that language. And then there are other models which have been, and they have some successes, but they may have some let's say, cons for other specific data sets. Like I mentioned, this issue of having a faster universe cosmological expansion in the early universe, in the early times, let's say. But then we have the downside of large-scale structure formation. That's why we really need to think about these models as their effect on what's happening to these parameters over time. So I don't know if I answered the question, but these are the points to think about, let's say.
Thank you very much. Yeah, I just wanted to say that to my view, just to respond to what you said, that I think, for example, hybrid models that combine some version of dark matter and like MOND in its classical limit, they can actually solve lots of things that you talked today about, for example, Hubble tension. So they have cosmological models that combine sterile neutrinos and MOND. And I don't know if you have a view on this kind of debate, but there's a paper by Banik from Indranil Banik from I think it's 2021, where they talk about hydrodynamical simulations for that things, for the hybrid models, and they do the comparison of all the problems that, well, some of the problems that you mentioned and more. And one of the things they talk about is the void and Hubble tension. So you know this work?
Yeah, not that paper in particular, but the general topic, yes. So here I'm trying to just give a picture from the Cosmoverse network. So I don't want to express any opinions about any particular models. But talking about MOND, I mean, MOND is the limit, let's say, of what we would get when we have different kinds of modified models that have a non-zero extra element, let's say, when we're looking at the galactic scale, for instance, right, or the clustering of galaxies.
It works, yeah, the relativistic extension now, it works.
Exactly, but so that is, in a sense, the limit of what some of these models may give us. When we take that limit, it may look like MOND in that sense. Yes, it could be. There are positives and negatives of that, but here I'm just trying to stick, just to the general status, let's say, out of of the community from this network. So I wouldn't want to, we have people in this network who are working on that. Some are working in a positive sense, and then there are also some others working. To try, not to try and limit, but to understand the limits of these models or the negatives of these models. So that's why I don't, it's still an open question, is what I'm trying to say.
Yes.
And yes, it would be interesting to see, even on the galactic scale, what happens there. But here, we're really talking about the need of a new cosmological model. So not just on the galactic scale, but beyond that.
Thank you very much. Yeah, I just last thing was that I was talking about the cosmological model. It's a cosmological model that they developed based on MOND. So it's not just galactic scale. It's a cosmological model that solves Hubble tension and explains CMB and things like that. So like it was on galactic scale 10 years ago. Now there is a cosmological model. I
Yes,
just thought it might be
okay.
interesting because of you talk so much about the Hubble, like Hubble constant changing the value, and that's what they talk exactly in the paper also. So I thought it might be interesting to bring up. Thank you very much.
No, thank you. No, just on that point. No, I mean, there are many cosmological analogs of the classic idea behind MOND, like Tevis mentioned MOND. But whether they really solve Hubble tension, I would need a paper that includes the CMB, like the full sample, the full likelihood of CMB, because this is the thing, like we really need to analyze at base level all of these things, you know, at a very deep level. I mentioned Planck, so the full Planck likelihood. This is the question. If someone tells you they solve Hubble tension, we need to understand whether it can take, whether the analysis has been done using the full Planck likelihood or ACT, as I mentioned here, and then the late universe, whether if we use these different samples of supernovae like 1A and the many other samples that go along with it, whether those are all really explained in a consistent manner. So, I mean, I would be very hesitant about saying solves Hubble tension. I mean, I don't claim that any model solves Hubble tension. Anyway, thank you.
Thank you.
Yes.
Yeah, then we have a question. Federico, go ahead.
Yeah, thank you, Jackson. Thank you for your talk. I just have a clarificatory question, I guess. So you mentioned that the measurement based on astrophysics does not presuppose the lambda CDM model. And I wanted to ask you if you think there are at least some ingredients that because you know are taken from the cosmological model and the measurement in the sense that of expansion of the universe.
Federico, sorry,
we should be
lost
assuming that the
you.
universe is expanding,
Federico,
right?
Federico, sorry, we lost you for a couple of seconds, so can you just reformulate?
Okay, so I rephrase. Okay. So the question basically is if you think there are some ingredients from the lambda CDM model that are also presupposed in the measurement that based on astrophysics that is supposed to be independent, because since we are measuring the rate of expansion, somehow we are assuming the universe is expanding, but that seems to be something related to the particular model we are. I know many models are actually predict expanding universe, but not all of them. So I wanted to ask you what's your take on that. Thanks.
Yes, I think it's about whether any of these astrophysical processes or models or whatever, whether this inherits anything from cosmology, right? From lambda CDM. And this is the nice thing about studying the local universe, that no, they don't. So they don't need a value of lambda to be able to tell you how fast something is moving away. The rate at which is moving away. It's really because we have what's called standard candles, where in this case, the brightness of an event is really very standard, meaning it's a very specific value. So, no, we don't have any leftovers in a sense from our cosmological model. And this is a very important point. So we're not putting in any lambda CDM into that. So we can take that exact sample and test it against not just lambda CDM, but other models, scalar field models, f of t, whatever you want, you know. It's free of those cosmological models. There are data sets that have some, let's say, leftover assumptions from cosmology, but these are not those. So to answer the question, we really have a large number of samples which are cosmology free, totally cosmology free, which again emphasizes the point of this being a late universe versus early universe tension within lambda CDM. Okay.
So if I can just ask you a small point. So you're saying the data sets are free from cosmological assumptions,
Yeah.
but then the values, these data sets, the H0 value that these data sets allows you to infer, since H0 is a parameter that belongs to the models, that value it's again connected to the. I think that my question was more about the value of H0, not the data sets.
Okay, so just to clarify that, so yes, so the data set is cosmology free, so it doesn't depend on any of these things. But then how do we get H naught? So H naught in these models, H naught appears, yes, as a parameter of these models. But beyond that, H naught is a physical thing. It is the value, it is the rate at which the universe is expanding today. So independently from these data sets, you can infer that value without using the model. I think I understand your question now. So it's that value of H naught. Is that the same H naught we are talking about when we talk about lambda CDM? It is, because it is the rate at which the universe is expanding today. However, it's not that we take any equations or any assumptions. I mean, well, we take the cosmological principle, but we are not taking the assumption of lambda CDM. We're not using generativity. We're not using cosmological constant. We are measuring in a kinematic way, if that makes sense. The rate at which the universe is expanding at present. That's what the value of H naught from these cosmology-free data samples or results would be. So we are getting the same parameter, but it's not the same parameter in terms of the model processing. One is the spirit of H naught. It is the value of the expansion today, the expansion rate today. Whereas in the other cases, like in lambda CDM, we are talking about a parameter in the model. So, in fact, yeah.
Yeah, and that clarifies it. Thank you.
Very good. Very good.
Thank you, Jackson. Thank you, Federico. Okay, Marco, go ahead if you have a question.
Sorry, couldn't find the button to raise the hand on Zoom. I'm being very technologically not savvy today. I'm sorry about that. So thank you for the presentation. I do have a couple of questions. They're all related, so I'll try to formulate the first one and see where it goes. Jackson, you also talk about possible systematics, but so first of all, you're talking about systematics with respect to the measurement through the distance ladder, or systematics in the measurement of H0 through lambda CDM, so CMB, BAO, and so on. So do you think that it's still possible systematics in the distance ladder methods or no? Because Reese doesn't think so, for example, my understanding.
Yeah, that's true. But there are other people who still hold on to the idea that there may be some systematics at play, in particular in specific data sets. Let's say it this way, it's looking exceedingly unlikely that there will be some global systematic that takes away the tension entirely. It could be that there are specific data sets where maybe it could be reduced in some way, or either reduced or morphed. But I see it as very unlikely that this would totally disappear because of some systematic. Again, in this case, I mentioned 4 different kinds of, not just data sets, but phenomenology. So CMB and BBN from the early universe. And I also mentioned TRGB and supernova type 1A measurements. So it feels very unlikely that there would be something that would totally take this away. But as always, something could be wrong and this could be reduced. But taken away entirely seems exceedingly unlikely at this point. I think everybody would agree with that.
And then this leads me to the next part of the question. If so, I understand that distance ladder and cosmological model measurements of H0 are as independent as they could be in a sense. Like they don't rely on each other's assumptions, but they do rely on similar data analysis, right? So is it possible perhaps that the tools for data analysis, the use of simulation methods, the use of Monte Carlo simulation and so on and so forth, that could be not the resolution of the H0 tension, but impactful on the tension between different, the scientific assumptions are independent, yes, but not the data analysis that runs behind it. Is it a possibility? I don't know.
No. So the data analysis technique is Markov chain Monte Carlo. This is a very well tested. I mean, here I mentioned some applications from machine learning, and we hope that, you know, at some point we will be able to say something meaningful using machine learning. But if we're talking about MCMC, so Markov chain Monte Carlo, this is used all over science, and also it's built on very robust scientific statistical theorems in statistics and mathematics. I don't think we're going to find. I don't think it's that the data analysis is done incorrectly or something along those lines. Again, these are done by independent groups, using independent, you know, whether they use a model, no model, whatever. They're using very robust data analysis pipelines. So it, you know, not to throw cold water on that, but the data analysis is unlikely to be the source. What could be the source again? It could be that, who knows, whether we find some systematic somewhere, that may be, but not the way in which we do the data analysis. That would be very, you know, that would have much deeper repercussions across the world of science. So I don't think it will come from there.
So like to wrap up my three questions in a row, basically, it's like, okay, so not super likely that we're going to find relevant systematics with respect to distance ladder because we know the physics. It's independent of cosmological models, independent of the cosmological model. Then it's not very likely that we'll find systematics in the data models techniques because they're very well verified and quite robust with respect to the mathematics. And then we have a model that actually has quite several some holes in its scientific background, for example, cold dark matter, the problems that you were mentioning. So it seems to me like it really leads towards, oh, there is a problem with lambda CDM model, and that's it. So it's interesting to me so why is there still attention in, why are people still debating in science about whether it's cosmic, like why are not people convinced that, okay, so we need to modify the lambda CDM and that's it? Does it make sense?
So no, I think I get that. So why are we still talking about this? I think is the point. So let's say it this way: lambda CDM is an amazing model. I mean, if we look at the Lovelock theorem, as I mentioned here, it's really an amazing and in many ways very unique as a theory, as a model, and it has many successes. It's not that we should throw lambda CDM away. Lambda CDM explains a lot of observation. It is consistent with all surveys that we have today. The problem is between surveys, or possible problem. Now, why are people still clinging on to lambda CDM? If we lose lambda CDM, the cat is out of the bag. And there is no natural model, natural direction to go into. So we should always, until we have a new, what we can call concordance model, we should always have lambda CDM in all of these analyses, because without it, then there's no, there's no coherence in the community. So lambda CDM, whatever model, whatever new concordance model we will have at the level of the observations we are making today, these new models or new model will always have, let's say, a connection with lambda CDM. There will always be, if maybe not a limit, a mathematical limit to lambda CDM, the values will be very similar in essence. Even the value of H0, we're talking about high 60s versus low 70s. We're not talking about 150 to 500. So we still want the same sort of cosmology. We still want, CMB, want Big Bang, we want all of these things. What we want is just a better model of cosmology for these data sets, right? That's what we're talking about. So we still have to keep this, because then otherwise we have no way of, like I mentioned with the CMB, how do you interpret the CMB without lambda CDM? You have to pick another model, and these other models may have more positives in terms of H0 tension, but they may have more negatives in other areas. I don't know. I can't predict. It depends on the model. But this is why we still cling on to lambda CDM, because for all its faults, lambda CDM still has a lot of positives, and it is still the concordance model until we have something that can perform better against the broader set of data sets.
No, I was not suggesting that we should delete like our lambda CDM model. I was just saying, I was just curious about, well, like even from a philosophical point, just from a rational point of view, all points towards, okay, we need to look at the assumption of lambda CDM and better lambda CDM instead of looking for more systematic somewhere else, because it seems that there isn't. So maybe this is more of a philosophical debate. So I don't know if it's so much debated into the literature in science, like in scientific literature, whether we still need to, whether the lambda CDM is under scrutiny as a whole. While to me, if we analyze the data and the data set, it seems like, oh, yes, we do have some issues with the model. We just need to better the model. But it's not like we should not look for a resolution of the tension in some more exotic, or not exotic models, but some systematics, for example, in the distance ladder. No, that's so my question would be more like, oh, are there many people that still believe that distance ladder hides some systematics that would resolve the tension, or no? It's more a sociological question, if you may.
Yeah, okay. Well, there are many in the conferences we have. I mean, there are many. You can see how the audience can vary between distance ladder corrections, early time corrections, and all of these things. But let's say it this way: when we're talking about statistical models, we are talking about the philosophy of these models in a certain sense. When we move away from generativity on its own for cosmology, and then we'll put in lambda, for instance. What are we saying? We're saying that we retain all the philosophical baggage of generativity, right, as a gravitational model. And we put in this new open question now, philosophically, of lambda, of how this explains dark energy, and so on. And when I say that the philosophy is in the statistics, it's because, depending on what we change, and we have many options, as I'm showing here, we are changing our interpretation, our understanding of how this connects with the real universe, right? So it has a big sway over how we think about how the universe works, how it evolves, and how these models can develop onwards. I don't think that there's an answer to this. I think it's as you said, sociological, where we can where people feel we should go.
Thank you.
Thank you both. Thank you, Marco. Thank you, Jackson, again. If there are no other questions, then we thank our speaker. And
thank you so much.
Thank you. And yeah, we will reconvene again for the next virtual lab. Thank you very much.
Thank you.